So last time we did this experiment, we loaded up this rubber band with increasing weights. And so here we can see it with the fully laden weight attached to it. What we're going to do now is we're going to do the same experiment, but we're going to do it in reverse. So what I'm going to do is we've taken this measurement already. That was the last measurement of the previous experiment where we had the rubber band fully laden. What we're going to do now is we're going to start taking the weights off, and we're going to see the extension, measure the extension as we reduce the weight on the band. So now we've taken off 50 grams, and we'll make a measurement of the extension here. Okay, so we've done the experiment a second time now, but unloading the weights. So let's go and have a look at the spreadsheet and see what we get for the results. Okay, so here's the data in the spreadsheet. The masses are all in this column here, and we have the lengths that we measured all in this column here. And again, just like I did when we did the experiment before, I've included this value for zero mass, zero weight, with the length that we measured on the bench. Now, this column here contains the strain, and again, the formula for calculating the strain is exactly what we had before. The strain, the error in the strain, again, is the same formula we went through before, and similarly for the stress and the stress error. So if you're uncertain about any of those, go back and look at the video on Young's modulus, where we measure these and show the calculations for where the numbers come from. So we've now got another plot that we can draw of strain versus stress, and we'll plot the strain just as before on the x-axis and the stress on the y-axis, and we can add it to the plot that we had when we were busy loading the rubber band up. So remember, the only difference we've done here is that instead of adding weights to the rubber band, we're now taking weights away from the rubber band. And so here is the plot that we get. So the blue lines here are not fits, these are just curves that go through the data points. And this top line here that you can see, this is the line that we got from loading it, and this bottom line here is the line that we got from unloading it. So you can see that they start in the same point, they start at 0 at the origin, and they end at the same point here where we have the maximum load, but they're not the same line, and they're very clearly different. If we look here, because of course the weights were quantized and came in 50 gram units of mass, we have quantized stress, so we have the same stress in the loading curve as we were adding weights as the same stress that we have in the unloading curve. And so you can see here that there's a difference between them, and that difference is substantial. It's far, far larger than the error bars between them, and it's at least 3 sigma difference here, and then there's another 3 sigma difference here, and then probably 3 here, and then maybe it's 2, and it gets closer together here. But if you look at them as a whole, it's very, very clear to a very high degree of significance that this is a different plot to the one that we got from loading it. So we have a different relationship between these two plots, and there's a gap. And this gap between the two curves, or this effect where you get this gap between the two curves, is something called hysteresis. Okay, so we've got this strange hysteresis effect, and so to understand a little bit more about what's going on, let's imagine that this is our rubber band, and we have our weight mg attached to the bottom of this, which is causing a tensile stress. And so what we've got here is, if this is the original length of the rubber band here, this is L0, then this distance here is our extension delta L. And so if we look at this, we have our weight, and this weight, if you remember, is coded into our stress, because we have stress is equal to F perpendicular divided by the cross section. So our stress sigma, this is equal to sigma. Sigma here is proportional to the force that's acting on the rubber band, right? So the stress is proportional to the force, and if we look at our strain here, strain is equal to the change in length divided by the original length, and so what this means, and this is equal to epsilon here, too many wiggles, epsilon, and so here what we have is that epsilon is proportional to the extension, so the distance that this force has been moved. And we saw from our plot of this was stress and this was strain that we ended up with a curve that looked something like this, and then we had our second curve that came down something like that, right? And so this was the loading curve and this was unloading. So if we look at this, then stress here is proportional to force, and strain here is proportional to the distance that the force has moved. So the area, if I take a region of the plot here, the area here is going to be proportional to the work done. Or another way of putting it, it's the proportional to the work done by the force to expand the elastic band. So another way of putting it is it's the elastic potential energy. So what we've got here is the area under this loading curve is the amount of work that is stored in the elastic band as we stretch it, and the area under the unloading curve is the amount of energy that is released from the elastic band when we allow it to retract back to its original length. So what that means is we have a region here, and I'll use a different color to highlight it, and this area is proportional to the energy absorbed by the elastic band. And so this is what hysteresis is. The fact that if you take a material and you stretch it elastically and then allow it to retract back to its original shape, it will arrive back at its original shape. It arrives back at the origin here, and it starts at the same point here. But because of the way the force changes over time, what you end up with is you get back less energy than you put into the system. And that energy difference is stored inside the material, and it causes the material to heat up. And that heating is why, for example, Formula One tires, they do a few, in a Formula One race car, when they're having the race, they will actually do a few laps before they have the proper race to heat the tires up. And the heating comes about because as the tires rotate, they compress and expand, and that compression and expansion causes the rubber in the tire to heat up and become more sticky. Improves the traction control, and without those warm-up races beforehand, they'd actually be more accidents on the track. And in fact, if you notice, if you ever watch a Formula One race car race, or they may also do it in the ones they have here in North America, they will actually have warming heating blankets around the tire to heat them up. But in the race conditions, the tires are kept warm because of this effect called hysteresis. Okay, so here you can see that we've got an idealized stress-strain curve here for a material, and it's important to note that this can be any type of stress or strain. So what this shows is it shows a region here where we've got a proportionality, and so if this was a tensile stress and a tensile strain, this would be the region where Young's modulus holds. Now if we go beyond this, we have a non-proportional region here, and this is where increasing amounts of stress generate larger strains. So up until this point, the same amount of stress will generate the same amount of strain. Here, the same amount of stress will generate a larger strain. So it's characterized by a lower gradient, so it starts to curve. Then at this point here, this is what's known as the elastic limit. So an elastic deformation is one that if I add the stress and pile on the stress on the material up until this limit, if I then relax the stress and take it all away, it'll go all the way back down to zero strain. In other words, I will recover the original shape of material that I started with. Of course, as we know, it's going to have some hysteresis, so it might not go down by exactly the same path, but it will get back to having zero strain. Beyond the elastic limit, so out here, we get what's called plastic deformation. And in plastic deformation now, we're no longer at an elastic deformation, it's plastic. So here there isn't technically a modulus of elasticity because we're no longer doing an elastic deformation. And if I take it back from here, so let's change the color to match the original plot. If I take it back from here and relax it and remove the stress, then what may happen is I may get something like this, where I go back down towards zero strain, but I don't go to zero strain. In other words, I'll have some trajectory as I remove the stress, but it will not go back to zero. It will not go back to the origin here. It will go back to some non-zero strain at this point. So here I've got no stress, so I've stopped deforming the object. I've taken all the stress away, but the shape of the object now is permanently altered from what it used to be. And so that's a plastic deformation. Now, the interesting thing here is at some point this gradient, so here of course the gradient is getting very, very shallow, so even a small increase in stress can generate a huge increase in strain. So a small increase in the stress here can generate a very large deformation indeed. And at some point you reach the point of no return. So let's switch back to red here. So at this point here you've reached sort of the point of no return. Now what happens at this point is the material does not actually break. What happens is that in order to generate a larger strain, you need less stress. So if you add on the stress and pile it up till this point here, at this point, what will happen is the material will literally start to flow apart or move apart. And then, of course, what's happening now is that the strain is increasing, because if you keep the stress at this level, then the amount of stress that you need to generate larger strains is actually less than the stress that you're applying. So at this point, the material will start to flow. If it's a metal, it'll flow, and you get something called necking, and the material flows, and then eventually here, once you get to this particular strain, it will snap. Now, of course, if you get it up to this point and then remove the stress, you're going to have a very large plastic deformation, but the material will not break. Or if you get it up till this point and then drop the stress, instead of going back down here, what you might find is the material will move out towards here, but it won't actually break, as long as you remove the stress quickly enough that the strain does not exceed this this point here, at which point the material will actually fall apart and mechanically fail. Right? So, but this stress here, this is the largest stress that the material can bear without breaking, because if you apply this stress and hold it, the material will break. If you apply this stress and remove it, then you'll end up with a large deformation, but the material itself won't have actually fallen apart. And so this stress here is known as the breaking strength of the material. So it may be a tensile strength, in which case this is where you get the necking if you're pulling two parts together. But it can also be a compressive strength. At some point, if you apply a crushing force to concrete, at some point the concrete will crack and shatter and fail. The same with stone. And again, of course, it can be a shear stress. For example, paper has a very low tolerance for shear stress, and so here the breaking strength for shear stress in paper would be very low, and it's easy to pull it apart. So that's it for this plot, and we'll just have a quick discussion about breaking strengths. Okay, so we've seen how breaking materials have a breaking strength, and the value of that breaking strength doesn't just depend on the material, it also depends on the type of stress. So there's one of these stress versus strain plots for each type of strain and stress. So for example, if we go back to something we've already looked at, which is paper, if we take paper and subject it to a tensile stress, it's quite strong and has a quite high tensile breaking stress. Similarly with compression, in order for me to push a hole in the paper, I'd have to really press extremely hard, far more than I can manage with my fingers, in order to make a hole for a compressive failure. So the compressive strength of paper is also relatively high. But as we've seen before, if we look at the shear strength of paper, so in other words the shear stress that's required to make paper fail, it's not very much at all, right? So that's an example of a material with a high tensile strength, a high compressive strength, but a very weak shear strength. And other materials have different properties. So for example, concrete has a very high compressive strength, but not very strong tensile strength. And in the next module, when we deal with liquids, we'll see that they can have quite a high compressive strength or bulk strength, but they have a very, very low tensile strength. In fact, zero tensile strength. You can easily pull a liquid apart. Now, to get back to the problem we posed right at the start of this module on elasticity, we asked, when we drop a mobile phone, why is it that some of the material, like the glass front, shatters, but the metal backing just gets dented and scratched? Well, we can classify materials into one of two types, ductile and brittle. Now, metals are generally ductile, and so if we take a metal, what a ductile metal like this sheet here, a ductile material has a breaking strength that is a lot greater than its elastic limit. So if you think about that curved stress-strain plot, the limit of elastic stress, right, so this was the limit where when we relax the stress, it goes back to its original shape. The elastic stress limit is a long way below the breaking stress limit, and so we can easily exceed the elastic limit without exceeding the breaking limit, and then we get a plastic deformation, and so that's a permanent deformation of the material without it breaking. So for example, with this metal sheet, which is a ductile material, I can easily exceed the elastic limit. I've removed the stress now and it's not returned to its flat position. I permanently deformed it. I've made it undergo a plastic deformation, but it hasn't broken. So this is a ductile material. Now if I take a pencil lead here, which is graphite, this is a brittle material, which means that although I can elastically deform it, you probably can't see it here, but I can bend it ever so slightly without it breaking. If I bend it very much at all, it will snap like it did there. And that's an example of a brittle material where the breaking strength is very, very close to the elastic limit, and so it's very hard, if not impossible, to actually plastically deform these materials. Now, although it appears that if you elastically deform something, it returns to its original shape, it is actually possible for a material to fail, even if you don't get up to the breaking or even elastic limit, by a process called, for example, metal fatigue, if it's in metals. And this is what was found in the early 1950s and 60s in the jet industry, in the jet aviation industry, where the stresses on plane bodies were sufficient, although they were elastic and thought to be well within limits of what the metal could withstand. The continuous elastic deformation when planes took off and landed caused microfractures to occur inside these metals, leading to their failure, and this was behind several early air disasters, until they realized that in fact the limit that you can stress a metal to without causing any damage at all is in fact less than the elastic limit. But this only applies when you're continuously, repeatedly stressing the material and relaxing, stress, relax, stress, relax. You get these microfractures. So that's it for the module on elasticity. We'll finish there before we get student fatigue from repeated talking about stress.